geodesic. This is the curve for which the action is minimized. This is the shortest curve. Well, usually we write, let me write those equations of geodesic. So these are, well, let's do this plus, well, let me put it this way. Gamma I, j, k, that depends on q, j, k equal to 0, and there is a solid j, k. So that's the equation of geodesics. When these gammas, they call Christoffel symbols, they'll be exactly this combination of metric and its derivative. Well, I can write what it is. It's 1/2 g I m dj. Well, this d within it means d by the derivative. G m j k. Yeah. And this must be G. Yeah, well, these are Christoffel symbols. And, well, I'm going to derive them in a second, but because they enter the equation of geodesic in a specific way, then, well, this is symmetric in J and K. You don't really need to pay that much attention to this, but you have to understand how this was derived. And so that this is obtained by taking the first derivatives of the metric. So if the metric is constant, this is just 0. Okay. So these are one-dimensional variational problems. Yeah, and now I want to turn it to another form. So I'm going to define, so you could write, this is Lagrangian equation. This is Lagrangian formalism. There is another formalism that is called Hamiltonian. So here the basic variables are coordinates and velocities. In Hamiltonian formalism, the variables are coordinates and momentum. So the first thing you do, you introduce momentum. So in momentum, exactly this quantity. So you say, well, let's call it, well, in this book they call it C, let me call it P, like in physics books. So Pi is dL by d q over r. So these are generalized momentum. Well, of course, for that simple example of mechanics, this would be exactly m times the velocity. But in general, this could be something else, but something. And L depends on Q, and Q dot, right, on coordinates and velocities. So the idea is now to invert this and express the velocities as some functions of coordinates and momentum. So basically that, well, of course, this is some function of q and q dot, right? So the question is whether you can invert it. Well, suppose that it is possible. And when will this be possible? Well, this is possible when, well, this is some function, right? So you have p I, and that's some function that depends on Q and, well, Q dot. Okay. So if you take the Jacobian like this, then this will be, well, let me just write it in terms of that. So just take the derivative of that with respect to Q dot. Then this is second derivative of the Lagrangian with respect to the velocities. Okay? So look at that matrix. That's exactly this Jacobian. So this will be invertible locally if this Jacobian is invertible. So that is this matrix. And it has a name. This is called Hessian. For those examples that we had, remember that Lagrangian was quadratic in velocities. So for if L is 1/2 Gij Q dot I Q dot J or minus V, what will this be? You take second derivative of L. Well, if you compute the first derivative, we already did it. It just 2 cancels that, and you get Gij Q. And then you compute another one, you'll see that this is exactly the metric. And we assume that it is not degenerate. So if the metric is not degenerate, then you do indeed, you can invert this and express the velocities in terms of the momentum. And so your basic variables become now the momentum. Okay? So what in the beginning, I called it phase space. I cheated a little bit because the phase space, well, in usual mechanics, momentum differs from velocity just by mass, by constant. But in general, it may be very different. And so the phase space is that. It's the set of coordinates and momentum. And those of you who took differential geometry, then you know that